Welcome to our session on data pre-processing and post-processing, a crucial skill often referred to as data massaging. In the realm of scientific computing and data analysis, we frequently encounter data files that are not immediately ready for our intended use. These files might come from experiments, simulations, or various digital sources, and they often require transformation to meet specific objectives. This lesson is designed to equip you with the ability to develop flexible Python scripts for several common data post-processing tasks. We will explore why such massaging is necessary, looking at how it facilitates visualization, helps in abstracting essential information from large datasets, and prepares data for further analysis or presentation. Our learning journey will involve understanding different data file formats, including standard ones like the XYZ format, and more non-standard, or wild-type, data structures. We will then dive into practical examples, demonstrating step-by-step how to write Python code to read, manipulate, and reformat these files to achieve desired outcomes, effectively turning raw data into a more usable and insightful form. Let us begin by looking at a simple example of a formatted data file type, the XYZ format. This format is widely used in computational chemistry and molecular modeling to represent atomic coordinates. As you can see in the provided image, an XYZ file typically starts with a line indicating the number of atoms in the system. The second line is usually a comment line, which can contain any descriptive text. Subsequent lines then detail the atomic information, where each line represents a single atom. Typically, each of these lines includes an atomic symbol, like C for carbon or H for hydrogen, followed by its X, Y, and Z Cartesian coordinates. These coordinates are numerical values that specify the atom's position in three-dimensional space. One of the conveniences of the XYZ format is its simplicity. You can easily view or even edit these files using any standard text editor, such as Notepad or WordPad, as they are plain text files. For more detailed specifications, you can refer to resources like the Wikipedia page on the XYZ file format. Here we see a practical application of the XYZ file format. This image displays a visualization of a benzene molecule, which was generated using a software called VEMDE, based on data from an XYZ file. Each sphere in the visualization represents an atom, with different colors typically used to denote different atomic elements. The spatial arrangement of these spheres accurately reflects the three-dimensional structure of the molecule as defined by the coordinates in the XYZ file. This visual representation is incredibly useful for understanding molecular geometry, interatomic distances, and overall molecular architecture. It demonstrates how a simple text-based XYZ file containing atomic symbols and their coordinates can be transformed into a rich visual model that aids in scientific analysis and communication. To bring these XYZ files to life visually, we can use specialized software. A very popular and powerful tool for this purpose is VEMD, which stands for Visual Molecular Dynamics. VMD is capable of reading XYZ files, among many other formats, and rendering them as interactive three-dimensional models, like the benzene molecule we just saw. It allows for various visualization styles, measurements, and even animation of molecular trajectories if you have a sequence of XYZ structures. For those of you who would like to use VMD, you can download and install it from the links provided. These resources will guide you to obtain the software, which is widely used in the scientific community for molecular visualization and analysis. Now, let us consider an example of a non-standard data file type, which we will call BK7S2.k. This file is not in a universally recognized format like XYZ, but rather has a structure specific to a particular application or calculation. In this case, the BK7S2.k file is used in calculations related to generalized Mie theory, which is a model describing how light scatters off particles. Such files often require custom parsing scripts to extract meaningful information. To work with this file, we first need to obtain it. The slide suggests downloading it from the provided URL using a Python command, specifically the requests.get function. This is a common task when dealing with data that resides on web servers or online repositories. This code block demonstrates how to download the bk7s2.k file from the specified web address. First, it imports the necessary Python libraries, OS for operating system interactions like checking if a file exists, and requests for making HTTP requests to fetch data from the internet. It defines the URL where the file is located. Then, the requests.get function is called with this URL, and the response from the server is stored. The content of this response, which is the actual file data, is then written to a new local file named bk7s2.k in write binary mode. Finally, the code uses os.path.ice file to check if the file has indeed been successfully created in the current working directory, and this check will return true if the download and save operation was successful. Remember, your computer needs an active internet connection for this code to execute correctly. Once we have downloaded the bk7s2.k file, our next step is to inspect its contents. We will use Python commands to open this file, read its data line by line, and then print each line to the console. It is important to remember that when Python reads lines from a text file, using a command like open, file2 open, r, and then read lines, each line is treated as a string of text. These are not automatically interpreted as numerical values, even if they appear to be numbers in the file. This distinction is crucial, because if we need to perform mathematical operations on any data from the file, we will first have to explicitly convert those string representations into numeric types like integers or floating point numbers. This process of reading and initial inspection is a fundamental part of data massaging. The Python script here opens the bk7s2.k file in read mode. It then reads all lines from the file into a list called raw data. After reading, the script iterates through each line in this list. For each line, it first removes any leading or trailing whitespace characters using the strip method. Then, it splits the line into a list of strings using spaces as delimiters via the split method. Finally, it prints this list of strings, which represents the content of that particular line broken down into its constituent parts. This output shows us the structure of the file line by line, revealing how the data is organized within it. Let us examine the content and structure of the bk7s2.k file more closely, which you can also view using any text editor. The first line, referred to as row 0, contains the value of the wavelength of the FTIR radiation. The second line, row 1, specifies the number of spheres involved in the scattering scenario. From the third line onwards, the data is organized into columns. The first column represents the x-coordinate, the second is the y-coordinate, and the third is the z-coordinate of each sphere. The fourth column gives the radius of the sphere. The fifth and sixth columns contain the real and imaginary parts of the refractive index for each sphere, respectively. Our task now is to convert this bk7s2.k file into the standard XYZ format, which, as we saw earlier, is suitable for visualization with VMD. The target XYZ file, which we will name config.xyz, should look like the example shown. The first line being the number of atoms, the second a comment line, and subsequent lines containing an element symbol followed by its x, y, and z coordinates. When faced with data manipulation tasks, it might be tempting to immediately turn to powerful libraries like pandas. For instance, one might think of using pandas.read_CSV to load the bk7s2.k file into a data frame. However, Pandas is most effective with well-structured, tabular data, often in formats like CSVS or similar text files with clear delimiters and consistent headers. The bk7s2.k file and many other real-world data files we encounter often have non-standard formats. They might lack proper headers, contain intermittent comments or metadata lines, or use inconsistent spacing that makes automatic column separation difficult for Pandas. In such scenarios, which are common in data massaging, relying solely on high-level tools like Pandas, data frames might not be straightforward or even feasible. Instead, a more manual, line-by-line processing approach using basic Python file operations often provides the necessary flexibility to handle these wild-type data files effectively. In our first practical example of data massaging, we will perform a customized data format conversion. The goal is to transform the bk7s2.k file, which has a non-standard format specific to its original application, into an XYZ format file that we will name bk7s2.xyz. The XYZ format, as we have discussed, is widely recognized for representing molecular coordinates and can be easily visualized. The Python code that follows will demonstrate precisely how to achieve this. It will involve reading the source file line by line, selectively extracting the required information, such as the number of particles and their coordinates, and then reformatting this information according to the XYZ file specifications before writing it out to the new bk7s2.xyz file. This Python code performs the conversion from the bk7s2.k format to the XYZ format. First, it opens the input file bk7s2.k in read mode, reads all its lines into a list called raw data, and then closes the file. Next, it opens the output file bk7s2.xyz in write mode. The script then extracts the number of atoms from the second line of raw data, which is raw data, removes any whitespace, and prints it. This number of atoms is also written as the first line to the output XYZ file. A predefined comment line, sample comment line, is printed and written as the second line of the XYZ file. After these header lines, the code iterates through the rest of the raw data list, starting from the third line, which contains the actual coordinate data. For each of these lines, it removes whitespace, splits the line by spaces to get individual values, and then constructs a new line in XYZ format. This new line consists of a label C, representing carbon, followed by the X, Y, and Z coordinates extracted from the input file, specifically the first three elements of the split line. This formatted line is printed to the console and written to the bk7s2.xyz file. Finally, the output file is closed, completing the conversion. After running the previous code block, the file bk7s2.xyz should have been created and saved in your current working directory. To ensure that our data conversion task was performed correctly and the output file has the desired XYZ format, we will now read in this newly created file and print its contents to the screen. This verification step is crucial in data massaging to confirm that the script behaved as expected and that the resulting file is well-formed and ready for its intended use, such as visualization with VMDE or further processing. This Python script is designed to verify the contents of the bk7s2.xyz file that we generated in the previous step. It begins by opening this file in read mode. Then it reads all lines from the file into a list called raw data. The script then iterates through each line in the raw data list. For every line, it uses the strip method to remove any leading or trailing whitespace characters, such as newline characters, and then prints the cleaned line to the console. This allows us to inspect the structure and content of the bk7s2.xyz file directly and confirm that it matches the standard XYZ format we aimed for, with the correct number of atoms, the comment line, and the subsequent atomic data lines, each containing an element symbol and its 3 coordinates. Let us move on to a second example of customized data format conversion. This time, we will be working with 2 input data files. The first is named gmt.date, and the second is experimental.date. You will need to download both of these files from the URLs provided. The slide shows a glimpse of the first few lines of each file to illustrate their structure. The gmt.date file contains wavelength and cxt values, which represent extinction cross-sections. The experimental.date file also contains wavelength and cxt values, along with other data like refractive indices and scattering and absorption cross-sections. Our task is to take the numerical values from the cxt column in gmt.date and use them to replace the corresponding cxt values in the experimental.date file. The resulting modified data will then be saved into a new file named experimental_mock.date. This scenario mimics a common task, where data from one source needs to be integrated or used to update data in another file. This code block performs the task of merging data from 2 files. First, it ensures both gmt.date and experimental.date are downloaded from their respective URLs using the requests library and saved locally. It then opens both these files for reading, loading their contents line by line into data.exp and datag.mt lists respectively. The script then prepares to write to a new file called experimental_mock.dat. It starts by writing the first 2 header lines from the data.exp list directly to the output files. After that, it iterates through the lines of data.exp, starting from the 3rd line, which is index 2, as the first 2 lines are headers. In each iteration, it also accesses the corresponding line from datag.mt. It extracts the second column value, which is the cxt value, from the current gmt.date line. It also splits the current experimental.date line into its components. A new line is then constructed using the wavelength, real refractive index, imaginary refractive index from the experimental.date line, followed by the cxt value extracted from gmt.date, and finally the cabs value from experimental.date. This newly constructed line, with the cxt value replaced, is written to experimental_mock.date. The process repeats for all data lines, and finally, the output file is closed. To confirm that our previous data massaging operation was successful, this code block allows us to inspect the beginning of the newly created experimental_mock.date file. It opens this file in read mode and reads all its lines into a list called raw data. Then, it iterates through the first 6 lines of this raw data list. For each of these initial lines, it removes any leading or trailing whitespace using the strip method, and prints the cleaned line to the console. This will show us the header lines and the first few data lines of the modified file, allowing us to verify that the cxt column, which is the 5th column of data, now contains the values sourced from the gmt.date file, while other columns retain their original values from experimental.date. Our third example focuses on a different kind of data massaging task, reducing and abstracting data from a large simulation output file. We will be working with a file named silicene.lamstry. This file is in the LAMMPS trajectory format, which is commonly used in molecular dynamics simulations to store snapshots or frames of a system's state at different time points. The LAMMPS data format itself is quite detailed, and you can find more information about it via the provided link. The specific silicene.lamstry file we are using contains multiple frames representing the dynamics of a silicene sheet. This data originates from research published in the IOP Science Journal, as referenced. Before we process it, it is helpful to visualize such trajectory files with a tool like VMD to get a feel for the data they contain, which typically involves atomic positions evolving over time. Here, we have an embedded video that visually represents the content of the silicene.lamstry file. This video, likely generated using VMD or similar visualization software, shows the dynamic behavior of the silicene sheet over the course of the simulation. You can see the atoms moving and the structure evolving. Watching this helps to understand what a trajectory file captures, which is essentially a movie of the molecular system. This visualization underscores the importance of such files in studying time-dependent phenomena at the atomic scale, and also motivates why we might want to abstract specific portions of this data for closer analysis or for creating shorter, more focused visualizations. If you are unable to view the embedded video directly within the Colab notebook, perhaps due to internet connectivity issues or browser limitations, an alternative is provided. You can download the video file from the given URL. Once downloaded to your local computer, you can play it using any standard video viewing application, such as VLC Player or your operating system's default media player. This ensures you can still see the visualization of the silicene trajectory, which provides valuable context for the data massaging task we are about to undertake with the silicene.lamstry file. Now let us define the specific task for our third example, involving the silicene.lamstry file. First, we need to write a Python script that can count the total number of frames, or snapshots, contained within this large trajectory file. Each frame represents the state of the system at a particular time step. Second, after determining the total number of frames, our script should abstract a smaller subset of these frames. Specifically, we aim to extract approximately the first 8 snapshots, though a slight variation like 7 or 9 is acceptable, and save them into a new file named silicene_8.lamstry. A useful hint for identifying the start of each new frame or snapshot within the lamstry file is to look for the keyword time step. This keyword typically marks the beginning of a new block of data corresponding to a single frame. After creating the smaller trajectory file, you should verify its correctness by visualizing it with VMD. This code block handles the download of the silicene.lamstry file, which is necessary for our data massaging task. It begins by importing the requests library, which is essential for fetching data from web URLs, and also matplotlib.pyflot, although it is not used in this particular snippet for downloading. A URL pointing to the Google Drive location of the silicene.lamstry file is defined. The requests.get function is then used to retrieve the content from this URL. The response object R contains the file data, and R.content accesses this data in bytes. Finally, the script opens a local file named silicene.lamstry in write binary mode, indicated by WB, and writes the downloaded content into it. This ensures we have a local copy of the trajectory file to work with in the subsequent steps. This Python script performs the data massaging on the silicene.lamstry file. First, it opens the file, reads all lines into raw data, and closes it. It then identifies the starting line number of each snapshot or block by searching for the time step keyword, storing these starting line numbers in the begin list. The total number of blocks and the length of a single block are printed. The script aims to abstract a specific number of frames, in this case, 7 frames, spread out across the entire trajectory. It calculates an interval, deltan, to sample frames somewhat evenly from the total number of frames, nf. It then opens a new file, silicene_8.lampster, for writing. The code iterates n times, which is 7 in this instance. In each iteration, it selects a frame based on the calculated interval. J equals I times deltan. It determines the end line of this selected block and writes all lines belonging to this block, from its starting line, begin, to its end line, into the new output file. After writing all selected frames, the output file is closed. To quickly check the output of our previous data massaging script, this code block reads and prints the first few lines of the silicene_8.lampsterjs file. It opens the file in read mode, reads all its lines into the raw data list, and then closes the file. It then iterates through the first 12 lines of raw data. For each of these lines, it removes any leading or trailing whitespace using the strip method and prints the result. This allows us to verify that the new, smaller trajectory file has been created and that its header and the beginning of the first frame appear to be in the correct LAMMPS trajectory format, confirming that our abstraction process has worked as intended, at least for the initial part of the file. After creating the silicene_8.lampstrace file, which contains a subset of frames from the original trajectory, a crucial verification step is to visualize it. You can do this manually using the VMD software. Open VMD, load the silicene_8.lampster file, and ensure that it displays the silicene structure correctly and that you can navigate through the abstracted frames. This visual check will confirm that the file format is intact and that the data massaging process has successfully produced a valid, viewable trajectory file containing the intended number of snapshots. In this lesson, we have explored the essential concept of data massaging, which involves pre-processing and post-processing data files to prepare them for specific tasks. We saw that real-world data often comes in non-standard formats that require custom handling, contrasting this with well-structured formats like XYZ. We learned how to use basic Python file operations to read, parse, and manipulate data line by line, providing the flexibility needed for such wild-type files where tools like pandas might be less straightforward. Through practical examples, we converted a custom formatted file to the XYZ format for visualization, merged data from 2 different files by selectively replacing columns, and abstracted a subset of frames from a large LAMMPS trajectory file. These examples illustrated how Python scripting can be a powerful tool for transforming raw data into a more usable and insightful state, a fundamental skill in any data-driven scientific endeavor.